Welcome to Control Systems Lectures. We continue with our lecture on modeling in the frequency domain. In the previous lecture, we looked at rotational mechanical systems. We derived the equations that relate the inertia, the viscous damper, and the rotational spring. And we're able to see that rotational systems can be modeled using those three elements. In this lecture, we will consider now rotational mechanical systems with gears. Gear systems are very important in engineering systems where we transmit rotational motion to another rotational motion, or from rotational motion to a linear motion. And this is very important for transmitting energy from one system to the other. The gear system we're going to look at is an ideal gear system in the sense that there is no backlash and is lossless, so it does not absorb or store energy. So these are the conditions or the assumptions that are guiding the formulation of the equations we're going to have. When we say there is no backlash, it means that the teeth of the gears is perfectly merged and there is no any play between them. So the movement of gear 1 or the driving gear will be transmitted exactly the same to the movement of gear 2. So here we have the two gears where you have your input gear and you have your output gear. The input gear is got n number of teeth. The output is got an n2 number of teeth. And then we have the radius of the input gear to be R1 and R2 is the radius of the output gear. So the input gear is called the drive gear and the output gear is called the driven gear. The torque applied to gear 1 is T1 and the angular displacement is theta 1. And on the second gear is theta 2 T2. The distance moved through the circumference of the drive and driven gears will be the same. So since we say there is no backlash, it means there is perfect meshing here. So the movement of this gear will be equal to the movement of the gear 2. So we can write R1 theta 1 is equals to R2 theta 2. So from here we get the ratio R1 over R2 is equals to theta 2 over theta 1. The ratio of the number of teeth, which is designated as n, is in the same proportion as the ratio of the radii. Therefore, we can write that since we say theta 2 over theta 1 is equals to R1 over R2, and since the teeth on the number of teeth is directly proportional to the radii, then R1 over R2 will be equals to N1 over N2. Then based on assumption 3, where we say that the gears does not lose or absorb energy, we said that the energy input gear 1 will be equals to the energy into gear 2. And the equation for energy is torque multiplied by the angular displacement. So the torque to gear 1 multiplied by the angular displacement of gear 1 will be equal to the torque on gear 2 multiplied by the angular displacement on the second gear. So we can now have the ratio T2 over T1 is equals to theta 1 over theta 2 equals to N2 over N1. So these are relational equations that we can use to model our gear system. So if you take, for example, the transfer function for the angular displacement. So if you take angular displacement with the gears, so you have theta 1 over theta 2 is equals to N2 over N1. So N1 is equals to N2 over N1 theta 2. So if you put that in a block diagram form, you have your input theta 1 and you have the transfer function will be N1 over N2, which is the ratio of the gears, and the output will be theta 2. Remember what we said about block diagram, that the arrow in means that the quantity here multiplies by what is in the box, and out here will be equals to theta 2. So if you're going to write the equation from the block diagram, it will be theta 1 multiplied by n1 over n2 is equals to theta 2. Again, you can also have the transfer function for torque in ideal gears as T1 being the input, and you have n2 over n1 as your transfer function, and then T2 will be the output. So here you have T1 multiplied by T2 over n1 is equals to T2. Now let's look at this mechanical system. In this system, we can see that these gears are driving rotational inertia, viscous damper, and a spring. For clarity, this is the gear N1 and this is N2. We're just looking at the N views, and that's why we represent them in this way. And because N1 and N2 is perfectly merging, this will give us a 1 degree of freedom. Now, what do we want to do? We want to represent this system as an equivalent system at theta 1. So we want to see how do we represent this side of the system as an equivalent system at this end. So first we represent T1 in terms of T2. So T2 will be T1 N2 over N1 multiplied by theta 2. So if you come here, you will represent this by T2. T2 will be the torque at this point. And the torque here, because you have two gears, so T2 will be N2 over N1 T1 based on the ratio. So we have represented that there. So this is equivalent system at the output after reflection of input torque. So we have reflected the input torque. We now can develop our equation of motion where you can see that this is now the equivalent side. So J S squared plus DS plus K multiplied by theta 2 will be equals to the input torque, which is T2. And T2 is this, what we've represented here as an equivalent torque. So you can see that from this equation 1, we know that T2 is N2 over N1 multiplied by T1, and theta 2 is N1 over N2 theta 1. From those relationships, we substitute this into equation 1, and we have Js squared plus ds plus k. In place of theta 2, we have N1 over N2 theta 1. This is equals to, in place of T2, we have N2 over N1 T1. This gives us equation 2. And then we multiply all through with N2 over N1. In that case, we have N1 over N2 square. And we multiply all through by N1 over N2 so that this cancels out. And therefore, this gives us N1 over N2 square. Theta 1 equals to T1 T1s. This gives us equation 3. And if you put this into this equation, you have Js squared N1 over N2 square plus ds N1 over N2 square plus k N1 over N2 square. So equation 4 gives the equivalent system at the input. And this can be represented in this form. So you see we have the input. If you reflect this ratio on this impedances on the right hand side, then this gives us an equivalent system at the input after reflection of the impedances. So we can generalize the result by saying that rotational mechanical impedances can be reflected through gear trains by multiplying the mechanical impedance by the ratio. And we're talking of the ratio of the teeth of the gears. So we will have number of teeth of gear on destination shaft over number of teeth of gear on source shaft or the drive shaft. This is the driven and this is the source or the drive shaft square. You can see that's what we have here. And so if you try to make sense out of this, let me go backwards and show you this is what we have, and we wanted to reflect this whole side as just an input here so that we have like one system, and then we can easily derive the equation. So what we did was to reflect our torque, which this becomes now T2 theta 2. So if you have T2 theta 2 on this side, you are now reflecting all your you have a system that is an equivalent at the output after reflection of the input torque. So you have the input torque, and then from there you arrive at this equation. And so what you have is a simple system that you've reduced to this form, and you have the generalized form. So in this example, we want to find the transfer function theta 2 over T1. So we know that theta 2 will then be the output and T1 is the input. So if you look at our rotational mechanical system, which is shown with the gears, so we have the rotational system with the gears are meshed here, and the first thing we need to do is how do we reflect the torque and impedances to the output shaft. All right, we want to reflect the torque and the impedances to the output shaft. So note that the two inertias are connected by the gear, hence we have 1 degree of freedom system, so we're going to have one equation. So now we reflect the gears here, we reflect the torques. So you can see T1 will be T2 will be T1 N2 over N1, and you have your theta 2. So after we reflect this, based on our previous example, our inertia here will be an equivalent, J equivalent will be a J1 will come with the ratio of the gears square plus J2, and then D equivalent will be D1, which will have the gear ratios plus D2, and then K equivalent will also have will just be K2, because if you look at the system on this side we do not have any K, so we only have D1 and J1. So now this is how you reflect the torque on the output shaft. And once we reflect it in this form, then it's very easy for us to write the equation, because it will be the J equivalent S square plus D equivalent S plus K equivalent, everything multiplied by the angular displacement theta 2 will be equals to your applied torque. So, and we now know that our J equivalent is this equation here, D equivalent is this equation here, and K equivalent is K2 because we don't have a K1. So we can write the equation of motion in this form: JE equivalent plus DE equivalent S plus K equivalent multiplied by theta 2, which is equals to N1 over N2 T1. We can now then, from this equation 5, we can write the transfer function as theta 2 over T1, which is what we want to get as our transfer function. This will be equals to N2 over N1 over this part of the equation, which is J equivalent S square plus D equivalent S plus KE. So this is the equation of motion we're looking for, and then we can write our transfer function in this form where we have T1 as the input, theta 2 as the output, and of course our transfer function will be this part of the equation. I hope this is very clear. Otherwise, during the contact session, I can explain this further. So if you have a cascaded gear train, so you have N1, N2, N3, N4, N5, N6, and you want to reflect all these inertia as we have done in the previous cases, you will see that when you have only n1 and n2, your theta 2 will be n1 over n2, the ratio n1 over n2 multiplied by theta 1. So if you now want to reflect on theta 3, then theta 3 will be n3 over n4 multiplied by theta 2. And theta 2 we know is n1 over n2 theta 1. So if you substitute for theta 2, you will have n1, n3 over n2, n4 theta 1. The same thing goes on to where you come down to theta 4. And theta 4 will be n1, n3, n5 theta 1 over n2, n4, n6. You can see that there seems to be some kind of a pattern that is developing where the ratios of the odd numbers over the even numbers, n2, n1, n2, n3, n4, n5, n6. And so you have theta 4 is equals to, at the end of this system, you have your theta 4 to be equivalent to n1, n3, n5 over n2, n4, n6 multiplied by theta 1. So this is how you can cascade the gear train. Now we have gears with loss. We've been dealing with gears that do not have any losses, and now we have gears with a loss. So in this case, you have T1, theta 1, N1, and you have J1. Then you have N2, it's got its damping coefficients and also an inertia, and then you have N3. So from N2 to N3, and then N3, N4, and N4 also is got a J5 here, and there is a J4 here. Okay, so if you look at this problem here, we're supposed to find the transfer function theta 1 over T1. So first you reflect all the impedances to the input shaft theta 1. And if you reflect that, you will have your J equivalent will be equals to J1 plus J2 plus J3 multiplied by the ratio, because you can see that J2 and J3 are connected here. So it has to be J2 plus J3 multiplied by the ratio n1 over n2 squared. Same thing with J4 and J5, but this time around you see that the ratio will be n1, n3 over n2, n4 squared. And then the viscous damper equivalent will be D1 plus D2, n1 over n2 squared. And so you can also then write your transfer function where T1 is your input, theta 1 is your output, and you have 1 over J S squared plus D, J equivalent plus D equivalent S. So this is the end of lecture 206. I'm sure you will have questions, and I'll be ready to attend to them during our contact session. Thank you very much.